In particular, we talked about the wake and the concept of quasi-potential flow. And in particular, we have focused our attention on the potential flow unsteady formulation. And in particular, we emphasize the point that we have a differential problem in this domain. We have a very special domain like this, and we are looking for a boundary condition on the wake surface here. And this is the focus. This boundary condition were explored by considering a couple of principles to be applied through the supposed discontinuity. In particular, we have considered the mass conservation and momentum conservation through the wake discontinuity here, and we considered this quantity. In particular, if you multiply the density by the elementary area, dA, of this cylinder, we are here considering the mass penetrating, and if you multiply this relative velocity by dt, you have the displacement, this displacement here.
Professore, mi scusi, non credo stia presentando lo schermo.
Excuse me. Yes, thank you. And so we consider this quantity here, which is representing the mass. Here we have the density multiplied this elementary and infinitesimal area of this cylinder. We are considering this cylinder as a cylinder of fluid incoming inside this continuity surface. And so if you multiply this density by this infinitesimal area and this displacement, which is the relative velocity, by the delta t time, you are actually the mass penetrating in this circle of surface, and then we are imposing that the jump of this quantity be 0. Applying this, we found that necessarily the component of the velocity normal, the component on the normal to the forces, has no discontinuity, so delta Vn equal to 0. As a second quantity here, we have considered the momentum, and this momentum is again something like a density multiplied by again the infinitesimal area dA, and this quantity V by dt, let me emphasize this point, the relative velocity by dt is representing the infinitesimal dl, the length of this cylinder, and then the area by the dl by the rho is the mass of this infinitesimal portion fluid multiplied by the velocity. So this is the momentum, and the momentum are actually balancing the impulse of force. The impulse of force is given by the pressure by the dA again. So pressure by the area is the force, and you have to balance the momentum with the impulse force. The impulse is this by dt. Okay. Of course, the quantity dl or as dA or dt are unessential in this balance, and therefore applying the difference operator, we have obtained this consequence, and after this consequence, we add as a conclusion that we don't have any kind of pressure jump, and the two only possibility for the discontinuity is that the discontinuity does not exist. In that case, delta V, the jump of the velocity, is 0, or in the case you have a discontinuity, we have delta V not equal to 0, but this discontinuity of the velocity is represented only by a discontinuity of the normal component of the velocity, as here. Excuse me, only at the tangential discontinuity of the velocity, because the normal component of the velocity is not a discontinuous quantity. So at the end, we have two final conditions to be imposed. This here, no normal component of the velocity discontinuity, number one, and as consequence of number two, we have no pressure jump. So this and this. The question now is, how can we translate this condition in terms of velocity potential? Because we want boundary condition in here in terms of velocity potential on the wave. And in order to answer to this question, we have considered the Bernoulli theorem, and we have demonstrated that the Bernoulli theorem is not energy conservation, but is just conservation. In fact, if this is the statement of the Bernoulli theorem, this is the statement, let me write, equal to a constant in space, this statement is identical to momentum conservation or the Cauchy equation. In fact, if you take this equation, the gradient of this scalar quantity is just the momentum conservation, is identical to this here. Okay, and therefore Bernoulli theorem is actually representing in a scalar form for a potential flow, is representing the momentum conservation. Okay, now I want now to consider this number two consequence, delta P equal to 0, in the case of a flow, potential flow, and by considering a point just upper and lower to the wake. So here in one, you have the Bernoulli theorem in this form, the phi1 on the t plus, look, I am using this, and plus 1/2 the gradient of phi dot the gradient of phi, the velocity, this is v and v, plus p on rho in the point 1, so we have p1, phi1, phi1, and this is identical to the phi2 dt plus 1/2 gradient phi2 dot phi2 and plus p2 on rho. Rho is the same, is identical, of course, in the case of a compressible flow. So what happens in the point 1 is identical for the Bernoulli theorem in any time, is the same quantity in the point 2. Okay, and this is true because, as you know, for a potential flow, when you are here, you take this path integral is a path integral of point done by point which are all with zero vorticity. Okay. So what about the consequence of this? If you introduce the delta phi quantity as defined like phi upper minus phi lower, you have that by this equation that d delta phi, excuse me, we have that the time derivative, yes, the time derivative of delta phi, note that this delta phi quantity is a quantity defined in any time for x in the wake set, in the point of the wake, S wake. Okay, this is S wake. The S wake is a surface including all the point on the wake. Okay, so this function is a function defined on the wake here. You have a delta phi here, value, you have a delta phi here, a jump of phi, and so on. Okay, so if you move this quantity in the left-hand side, everything, you have this plus 1/2, and you have the gradient of phi1 dot the gradient of phi2 minus the gradient, excuse me, phi1 the gradient of phi2 dot the gradient of phi2 and plus delta p equal to 0, and this is p1 minus p2, but we have this condition to be applied, and so this is equal to 0. And what about this? Here we have the velocity in the point 1 just upper the wake dot the velocity 1 minus v in the point 2 dot in the point 2. And look, this quantity is something like a generalization of the famous rule of the algebra of the product of the sum of two quantity. Look, dot product, the difference of the same quantity. Okay. In fact, if you develop this scalar product, you have exactly this, because the mixed terms are able to be cancelled. And in fact, you have v1 dot v1 minus v1 dot v2 plus v1 dot v2, and so this is cancelled, and you have plus v2 and minus v2 dot v2. So this is the generalization of the scalar formula that you know very well. And therefore, instead of this quantity, we can find the following. We can find this interesting relationship. You have that the delta, the phi on dt plus v1 plus v2 vector divided by 2 dot v1 minus v2 equal to 0. Okay, and this is very interesting because we may define a velocity, a special velocity. Look, like v wake, and this v wake is the average between the upper velocity plus the lower velocity. So remember that we are considering this, and we're one here and two here. So this velocity is the average. And this average is an average from a quantity like this, okay, and a quantity like this, and you have to consider that the normal component is the same for. So we have two velocity with the same normal quantity, and therefore this average is something tangential to the wake. Okay, this is average velocity, and this vector is tangent to wake surface, because the normal component of V1, normal to the wake, is equal to the normal component of V2 because of this condition here. Okay, and so we have a strange velocity, and this velocity is defined, this is the definition, wake velocity. And if you consider this definition, you have the following from the previous relationship. The derivative of delta phi with respect to the time plus v wake dot the gradient of delta phi is 0. In fact, look, this is the difference of the velocity, but the difference of the velocity of the gradient of phi1 minus the gradient of phi2 is equal to the gradient of the difference, delta phi. And so this is the average velocity, the wake, and therefore we have this. And what is this? What is this representing? You have delta t a plus v wake gradient of a. What is this? Is anybody interpreting this formula? What this formula is talking about a destiny. This is sorry? What is this?
The Boltzmann transport equation.
Yes, this is a transport equation, and it is saying the following: if you are able to move with this velocity, the variation in time of the quantity a is 0. This is a convective derivative, and we can define this operator as the following: d is an operator, is a time wake derivative operator defined this way. And this operator is stating the following: if you are able to move tangentially to the wake with this velocity, with this strange velocity, and you are able to move by this velocity and consider what is the value of delta phi in that point, the value of delta phi does not change. In other words, physically, you have a body, and you have your contact discontinuity, the wake, okay? Wake or contact discontinuity. Now, here you have a delta phi, you have a jump in this point, okay? If you move on the wake with this velocity, this is an absolute velocity, okay? When we take the gradient of phi, we have the absolute velocity of the fluid, and here with v wake we are currently taking the average upper and lower, okay? If you move in this point with the velocity v wake, delta phi is constant. Okay, so delta phi is something, is a quantity which is preserved on the wake if you moves on the wake with VW velocity. And this is the statement of this condition. And this condition can be summarized as the following. The application of this operator on delta phi quantity is equal to 0. So, as a conclusion, there is something which is conserved in our problem if you move on the wake with this velocity. This velocity indeed is tangential to the wake, as we demonstrated. If you move on the wake, for example, we can move in the wake with the wake velocity in this way. Imagine that this is the trajectory of this motion, and time by time, moving on this line, delta phi is constant, is preserved. Okay? Of course, v wake is part of the unknown of the problem, because we don't know the potential flow, we don't know the velocity potential, we don't know the velocity, and so we don't know the wake velocity. So the determination of the wake geometry and the determination of this spatial velocity for applying this rule is part of the problem as well. And this is indicating the nonlinearity of with what we are describing. However, we have this new boundary condition on the wake to be applied on wake point, together with this other. This is a consequence of momentum conservation, Bernoulli theorem, and this is a consequence of the fact that delta p is 0, as we have demonstrated clearly, okay? And this is the second issue related to the momentum, and the first issue, again, is this here. Do not forget this, as consequence of a mass conservation. Delta Vn equal to 0. And delta Vn equal to 0 means, as a second condition, delta Pn equal to 0 means delta d phi, delta gradient of phi, which is the velocity, dot n, velocity projection on the normal of the wake, so this, but this is equal to delta, the normal gradient is also indicated with d phi on the n. Okay, this projection of the gradient in the n direction is d phi on the n, and therefore you can directly state that the derivative of d phi on the n of delta phi is equal to 0. So this is the second condition in this form, or in this form which is equivalent, to be applied together with the first one here. Okay, let me write this second like delta, no, red pencil, delta d phi on the end equal to 0. So we have finished. We have our boundary condition on the wake, and then we can recap together our differential problem to be solved. The problem to be solved is the following. We have final differential problem for phi. This is the body. This is our boundary. We have this. We have this. We have this. At limit, please consider this at limit. And we have this. And this is S at infinity. This is S. Where is it? This is S on the body. And please, attention. At the beginning, we have S wake prime. S wake prime are two distinct surfaces, one upper and lower. Look to my hand. This is S wake prime, but at limit, since the discontinuity has 0 thickness, you can take this limit of SW1 upper surface and SW1 lower surface. At limit, you have and this surface is a closed surface. Can you see the space inside here in my face? Yes. But at the limit, closer and closer and closer and closer, these two close surface becomes an open surface at the limit, only one. So at the limit here, you have the wake as the superposition at the limit of S wake 1 and S wake 1 upper and lower. So at the end, you have, after this limit process, you have a unique green here, a unique S wake as limit of S wake 1 and S wake 2. Okay. The normal to this surface, or the normal to this domain is the following. We have a normal to the body, we have a normal here, we have a normal here, a normal here. These are the normal vector to our domain at infinity, on the body, and on the wake. Attention, note that the normal vectors to the domain boundary are inward, not outward. Not okay, by definition. Okay, and so we have a domain D. We have the boundary of my domain indicated by the mathematician by delta D. This is for indicating the boundary, and this boundary is globally the union of S infinite union with S body union with S wake. And this S wake is just a sophisticated concept, the limit of S wake 1 going to from to be open to be from open to, excuse me, from close to an open surface, okay, at the limit. And here you have S wake. The differential problem is the following. We have Laplacian of phi equal to 0 in any time. Any time, wow, unsteady flow in any time and in any point x belonging to D. This is the differential equation, and the boundary conditions are V body dot n, body side, is equal to V fluid, but the fluid is the gradient of phi. And the gradient of phi dot n. This definition is the phi on the n, the normal velocity of the velocity potential. So this is the body boundary condition for x belonging to S body. First boundary condition. What is it? What is it? Yes, first boundary condition. The boundary conditions are with this color. For x on SB, S body. Second boundary condition, we have that phi is equal to 0 for x on S infinite. Here we have an unperturbed flow, so the velocity is 0, the gradient, so phi is constant, but this constant is arbitrary, and we can fix this constant with 0, okay? This is the second boundary condition at infinite. Third boundary condition, the wake. We have fixed this boundary condition, and we have that on the wake, the jump of the phi on the n is equal to 0 for x belonging to S wake. And what does it mean? No fluid penetration through the wake. Okay? So this is the third boundary condition on the wake surface. And the fourth boundary condition, the most complicated, is that if you take a special time derivative following a wake point is a point moving on the wake with the velocity d wake, okay? If you move on the wake with this or such a velocity and you evaluate delta phi, this delta phi is not varying if you move or such a velocity. And this is valid for any point x belonging to the S wake. Okay? Now, only now, we have completed the definition of our potential flow for unsteady compressible potential flow. Okay? So it's absolutely true that in your differential equation you don't have time. Yes, you don't have time here. This is true. But you have time as important and dependent variable for your boundary condition. In particular, here, the body in aeroelasticity, the body is moving. The wall are moving wall. for the aircraft, for the wing. So we have time here imposing an aesthetic boundary condition, but we have time here. Where is it? Point. And we have time here. Time. And these are the sources of unsteadiness in my flow to be considered. Okay? So I have completely defined my problem, and we have just to establish a link between what happens on the wake and what happens in the body, not here, excuse me, in the body, and the connection between what happens on the body here and the wake here are the following. You have to consider the trailing edge, because the trailing edge point is the point of connection between wake and body. And what about these two apparently independent boundary conditions applied on the body and applied on the wake? You have in such a way ensure a continuity of your problem, of your solution, and this is a zoom of the trailing edge. Okay? And you have a flow here, you have a flow here, and here you have the wake. Okay? And what you state in this point here is something like a continuity to be ensured, in the sense that the following: in this zone, if you take a picture in this condition here, you have, excuse me, here you have a value of phi in the x upper. U is for upper. You are in the upper surface of the airfoil here, and here you are in the lower surface of the aircraft. So you have a phi in a time x upper, and down here you have a phi lower in the point x lower, and here you have a delta phi on the wake, in the wake point. So how can we manage the continuity of the solution when you move toward the trailing edge? You have some continuity of the solution to be ensured, and the continuity is the following. If you consider, in red pencil, if you consider the limit for an x on the wake, an x on the wake is a point like this, a x of the wake going toward the trailing edge, in this, if you take this limit on the quantity delta phi the wake, this limit moving from here toward the trailing edge should be the limit of a point x in the upper side going to the x in the trailing edge of phi evaluated in the upper side, minus the limit of x lower going toward the trailing edge. Everybody is going to the trailing edge in this point, okay? But in the trailing edge point, at the limit, you should have that this limit should satisfy this condition, x lower. And what about this condition? We are saying that if you from here move toward this direction, if you from here move toward this direction and from here to this direction, you have that the jump of phi upper minus lower is exactly the wake jump going toward the trailing edge point. So this is something like a regularization of the solution, connecting the solution of the body with the solution of the wave. And this is the mathematical formulation of, do you know this regularity condition, the name of this regularity condition? Do you have any name to propose for this regularity condition? No, anybody? This regularity condition is also known as Kutta condition. Kutta condition. With Kutta condition, we are currently establish a relationship between the body boundary condition, the body surface solution, and the wake solution, in order not to have a discontinuity or singularity in the trailing edge point, which is currently a very special point. Okay? So what happens by this mathematical model, which is representing the physical model, we have, in the process of the flow, we have a velocity potential on the body, and this velocity potential in time is evolving in time, is developing in time, and time by time, you have that in the trailing edge, you have, from the body point of view, a discontinuity, and this discontinuity in the trailing edge became delta phi, upper minus lower, and this delta phi, by this wake condition, is convected on the wake geometry. This value is frozen and then moved on the wake. A number, you have a scalar number, 8, 9, 7.8 delta phi, and this 7.8 is moved on the wake. Okay, just like a tapis-roulant mechanism. You are generating the delta phi on the trailing edge, and then you have to move this delta phi, you have to convect this delta phi on the wake. And this is the story of quasi-potential flow differential problem. Okay? Just a second. Antonio, sto facendo delle lezioni di recupero. Abbiamo detto alle 10, ti va bene? Alle 10 o... Sì, ho mandato un'email a te e a Rino. Adesso mi fermo un attimo con la lezione, do un attimo una controllo. No, figurati, nessun problema. Ciao. Sì, ciao, ciao. Okay, so we can stop here. At this moment, we have our final differential problem. The next step, so look at the general step. We have formulated physically the potential flow in terms of primitive variable. In particular, with step one, so-called primitive variable or physical variable like pressure, velocity. And these are the four unknown. One unknown, the pressure distribution. Three unknown, the three velocity component. We have four unknown plus boundary condition. The four equations are conservation of the mass and momentum conservation. From the primitive formulation, step by two, we have formulated the potential, the velocity potential formulation. And now we have a unique unknown, the velocity potential, such that the velocity, absolute velocity, please, absolute velocity of the fluid is equal to the gradient of V. Okay? Now we are ready for the step number 3. And the step number 3 is integral formulation for phi. Okay? Next hour, and we have a break now. Thank you.
Sorry, Professor. May you stop the recording because I think that it crashed again.
Oh.
I see the clock stopped at 16 on my screen, so I don't know on yours.
No,
It's only
yes.
my problem.